Okay, so review. Right, if I hydrogenate an alkene, I'm going to reduce it to an alkane. So the two H's will add to each one of these carbons. Break the pi bond, an H goes on one carbon, H goes on the other carbon. And that's a syn addition. If we had anything, the two H's that go on would go on from the same side. For the reaction I've shown, you can't tell that, but that's how it would actually go. All right, so the reaction here is, first, all right, syn addition of the two H's. That's terrible. So if you hydrogenate an alkyne, first thing you get is the cis alkene. Then again, you've got an alkene here, you've got hydrogen and palladium, so this just keeps on going. And the final product is the alkane. And you want to make sure you keep your carbon count in there, right? You don't want to add a carbon in, take a carbon out. So if you treat an alkyne with hydrogen gas, transition metal, palladium, platinum, rhodium, nickel, you take the alkyne all the way down to the alkane. Combined with this reaction that I erased cleverly, right? If I take acetylene, C2H2, I can pull one proton off, put a carbon group on, pull the other proton off, put another carbon group on, and then hydrogenate that all the way down to the alkane. So if you use a reagent called, and this one sadly you just kind of have to memorize. If you use hydrogen and what's called Lindlar's catalyst, or if you want to call it a poisoned catalyst, it's basically a catalyst that's designed to interact with the alkyne, but not the alkene. So Lindlar's catalyst catalyzes the hydrogenation of alkynes, but not alkenes, and so the reaction stops here. So if you take an alkyne, hydrogen, and Lindlar's catalyst, you stop at the cis alkene. The thing to keep in mind there, because I'm going to show you one more reaction here. The thing to keep in mind, syn addition of two H's. And then just remember when you can stop. And like I said, there's no reason, Lindlar's the guy's name. It's palladium. So he takes palladium and he just added a ton of stuff to it. This is like, I don't know if you would consider, if you like working in an organic chem lab, this is probably fun to do. Take your palladium catalyst and just start adding crap to it until you see the reaction stop at the alkene. I think Lindlar's is like barium sulfate and quinoline. There's some acid in there. Like, it's just a mess of stuff, right? But what it's doing is it's preventing the alkene. The alkene suddenly is too bulky to sit down on the palladium hydrogenate its form. The alkyne, right, is bullet shaped. So it's a lot more sterically accessible. And I've done this where if you put too much on if the alkyne is too sterically hindered, it doesn't even reduce with Lindlar's, which is a pain if you need it to. All right, the sort of related one, so this, we have a way to go from the alkyne to the alkane. That's just hydrogen and palladium, same as chapter 8. A way to stop at the cis alkene, hydrogen and Lindlar's. If you use this, and I'm not going to go through this mechanism. It's in the PowerPoint show. It's a radical mechanism. It's a complex radical mechanism, but it will go to the transalkene. So if you use sodium metal in liquid ammonia, you'll reduce the alkyne to an alkene, to a transalkene, and this reaction mixture doesn't touch alkenes. Right? Same as Lindlar's catalyst, but for a different reason. So those are the three different ways to reduce an alkyne. You can go all the way to the alkane by using hydrogen and palladium, the same reaction you do with an alkene. You can stop at the cis alkene if you use a poison catalyst at H2, and again, that's just syn addition of two H's. And then you can do this dissolving metal. These are really pretty as well. You get a nice blue color. Sodium metal dissolved in ammonia is a really nice color. You can look for it on YouTube. Stops at the transalkene. That's a lot of just putting reactions in your head. But try to put it in a framework of these pi electron reactions. The last thing I wanted to show here, all these reactions, I mentioned this, right? The benzene rings don't do anything. The 3 pi bonds in the benzene ring are not touched. We don't know any chemistry in this semester. We're not doing any chemistry in this semester where you'll do anything to the benzene ring. Note how I'm phrasing that, okay? So I don't know what Amanda's going to do. She might hit you right off the bat with chemistry where the benzene does stuff. Okay, so benzene's more stable than you expect it to be, but it's not completely impervious to reaction. Questions? All right. Wipe your minds. Think about a sunny day or something. So, if you want to open up your exam, this is what, number 11 on exam 2. So I asked you for a mechanism, a rate law, the energy diagram, and the change you would make to accelerate the reaction. 11D becomes a legal question, I think. Because there were definitely some answers that read one way or right. They're just not the way I meant it. And since I was grading it, that's what was important. I'll explain that in a second. Okay, so I wanted to go through the mechanism. SN1, so you've got a good leaving group, no strong nucleophile or strong base. So bromide's going to leave. We're going to get a secondary cation. I think most folks did that all right. And then you need to have a migration happen. A methyl has to migrate, and that tripped a lot of folks up. All right, so the migration is really simple. And I'm not saying that to poke fun at you, I'm just saying it's really simple. Typically on these, if you guys find that you're drawing tons of arrows in a step, I'm not saying that's always wrong, but it's probably wrong. Like, think about the mechanisms we've drawn. It's like 2, 3 arrows. Here it's 1. So this methyl simply moves, or it could be any of the 3 methyls. You could draw that from any of them. But you don't need to show the electrons going to a carbon and then moving over here, and you don't end up with multiple charges. It's just 1 arrow. Methyl moves to this carbon. That's going to open up. That's going to make a tertiary cation. Talked to quite a few people who basically got to that cation, but through a really tortuous route. Lots of arrows, things moving all over the place. Really common mistake there. All right, and then, right, so now this cation, you can see pretty easily how it's going to get to the product. You need an ETO to add to the carbocation, and a lot of people just lost this proton, drew in ethoxide, right? But you can't, there's nothing to pull that proton off. Carbocations are strong acids, so this reaction is really being run under acidic conditions. Right, so you want to keep things protonated. You can make strong acids, but you can't make strong bases. And ethoxide is a strong base. All right, so ethanol attacks the cation. And the important thing here is that you keep that proton on there. And then ethanol or bromide, kind of whatever you want, can take that proton, and that gets us our product. If you did everything right, except you just went, if you said, and I think this is a fair number of you, you got to this cation correctly, and then you had ethanol attack. You had ethanol attack, not ethoxide, but you just said that this went to here. That's a deduction. It's like -3. Yeah.
Just a quick question. So, why not in the solution from the bromide ion deprotonate the ethanol?
Because it's just not a strong enough base.
Oh.
That's a good question. So I keep saying you got to have something take the proton. And yeah, it's really reasonable to say, well, you got a bromide there. Right, so if you think about this as an acid-base reaction, which it is, all right, so you have bromide minus react with ethanol. Both of those are weak bases, or a weak base and a weak acid. And you generate HBr, which is a really strong acid, and ethoxide, which is a really strong base. So it's not that that reaction can't happen, it's just that it doesn't enough for it to be practical. Again, if you look at pKa's, pKa of ethanol is about 16, pKa of HBr is about -3, give or take. All right, you're right around 20 orders of magnitude difference. So even in a mole, you've got maybe 1 ethoxide. Yeah, so like I said, you're not far off. If that's all you missed on this, you're not far off. But make sure, and I think this is probably the toughest thing about learning these mechanisms. When are you under acidic conditions? When are you under basic conditions? And what does that mean? All right, if you're under acidic conditions, all your intermediates need to either be kind of neutralish or strong acids. They can be weak bases, they can be weak acids, or they can be strong acids. Under basic conditions, they can be weak acids, weak bases, or strong bases. All right, I guess in the last minute or two, I'll put up the rate. If you look at this, the rate law for this should just be. So this was 5, I think. So the rate is just some rate constant times the concentration of 5. So answers that, like I say, probably get there. How would you accelerate the reaction? Well, you'd use more 5, right? If you put more 5 in there. Again, you're not really wrong, but that's not what I mean by accelerate the reaction. The other is you could start by making a tertiary. You could put the bromide on the other carbon, make a tertiary carbon, but it's not the same reaction then, it's a different reaction. Some people said you could add a catalyst. Technically true. A catalyst, that's what a catalyst does, is speed up the reaction, but you're not telling me what catalyst. The answer I was looking for, and this is one where I suspect you're just going to go away irritated with me. Really, the only answer I accepted was change the Br to an I. All right, so that's you make the leaving group better, the reaction goes faster. So out of all that, we're going to put together our diagram. We got energy over here, reaction coordinate. 5 is going to come in here. 6 is going to be not far off from that. A little lower maybe. Yeah, it's a little lower. Carbon, actually, probably a good bit lower. The carbon-oxygen bond is stronger than the carbon-bromide bond, but I don't think I took off anybody on that one. And now we've got 3 intermediates. So you need all 3 of those intermediates. So you're going to have steep, local minima, second local minima, third local minima down. So this is going to be A, B, and C. It'd be nice if you told me that these are transition states. And then, the thing I did look at in a little bit of detail, intermediate A needs to be higher in energy than intermediate B. Right? Secondary cation is less stable than a tertiary cation. So A should be higher than B. We still got, am I still in?
You have 13 minutes.
Okay. We won't be here 13 minutes. All right, so take a look at that. I'm in the office this afternoon. I'll be out front. I'll either be out front in Salem, or if you come into Salem and I'm not out at those tables, I'm in my office. Exam 3 is going to include Chapter 7, so review the Chapter 7 stuff. You know, what you did for Exam 2, you should review all that. I'm not saying you should redo every problem you did, because you got to learn new stuff. But I think, really seriously, and I'm not trying to blow smoke here, everybody is in position, like, almost everyone made some mistakes on the Chapter 7 stuff on Exam 2, but nobody just, I was like, you have no idea what's going on. So build on what you have. And I will see you either this afternoon or Tuesday.
Thank you.
You bet. See ya.